The next step is to translate this absolute flow velocity into the relative frame so we know how it will be impinging on our moving rotor blade. To do this, it's helpful to bring back our velocity triangle from the beginning and remember that we can calculate the relative flow velocity using the absolute flow velocity minus our rotate the movement of our reference frame. So we can say in the tangential direction, we'll do this component by component. So the tangential direction of our relative velocity, WU1, is going to be equal to CU1 minus U, which we've solved all of this already. We know that the tangential absolute velocity is 231 feet per second, and our rotational speed is 866 feet per second. So we're going to have a resulting relative tangential velocity of minus 634 feet per second. Looking in the axial direction, the axial component of the relative velocity, of course, is not going to be affected by the rotation of the blade, which is purely in the tangential direction. So we'll have the same relative axial velocity as absolute axial velocity. So that will still be 712 feet per second. We would also like to be able to calculate the relative flow angle, or the incidence angle to our blade, which is of course going to be beta 1. And to do that, we know that the axial component is 712 feet per second. We know the tangential component is actually in the negative direction here and going to be 631 feet per second. So our total W1 is going to have a magnitude just based on those two components, and we can also calculate our flow angle. So beta 1 is going to be the inverse tangent of WU1 over, oops, we got this a little messed up, don't we? The inverse tangent of WU1 over WA1. So inverse of minus 634 feet per second over 712 feet per second. So we get a flow angle here resulting of minus 41.7 degrees. And here I'd give you a word of warning, just since the tangent function is implemented differently in different places, it's not always guaranteed that if you do your signs correctly here for our flow velocities that you will get the correct sign on your flow angle. So it's helpful just to make sure that it makes sense. And so here we know we've got our velocity in a negative direction. So we would expect that our flow angle should be negative in this clockwise direction. And in most cases, that's exactly how it will be evaluated by your calculator. We also can calculate the actual magnitude of W1 here. So we can say W1 is, of course, the square root of WA1 squared plus WU1 squared. So we can drop in our numbers again. 712 feet per second squared plus minus 634 feet per second squared. So we'll get an absolute magnitude for our relative velocity of 954 feet per second. Next, we want to calculate the relative velocity at the exit of our rotor blade row. And so to do this, we have to remember that we were given a turning angle. We are told that the rotor airfoil will turn the flow by 17 degrees. So if we've got our inlet flow angle here at an angle of minus 41.7 degrees to axial, it's going to redirect our outlet flow by an angle of positive 17 degrees or 17 degrees closer to the axial direction, or in the counterclockwise direction. So normally we would say that, the turning angle delta 1, 2 is equal to the difference between the outlet relative flow angle and the inlet relative flow angle. So we can easily solve for our outlet relative flow angle just by reorganizing that and say delta 1, 2 plus beta 1. So our new flow angle is going to be 17 degrees plus a minus 41.7 degrees. So our new outlet flow angle is minus 24.7 degrees. So we've got an angle here now of minus 24.7 degrees. We can therefore calculate the new tangential flow velocity, or relative tangential flow velocity, WU2, just based on our velocity triangle here. We still know that we have the same axial component, WA1 is equal to WA2, and we're interested in finding our new value of WU2 here. So we can find that just by looking at our WA2 times the tangent of our flow angle here, beta 2. So we'll say that's again 712 feet per second times the tangent of minus 24.7 degrees, and so that'll tell us our new tangential velocity is minus 327 feet per second. Once again, it's good to pay attention to the signs. We've decreased the, or we've actually increased the tangential velocity so that it's closer to axial and closer to tangential velocity of 0, but it should still be negative based on our velocity triangles, and it is. So from this, again, we can calculate the absolute magnitude of our outlet flow velocity. It's again the square root of our components, since we've got a right triangle. So we're going to have minus 327 feet per second squared plus our axial component 712 feet per second squared. So the magnitude of our outlet velocity is going to be 784 feet per second.